All right, just a quick dive into chapter 13. This chapter covers ethers, epoxides, thiols, and sulfides. We will only touch on a few of our ether reactions and a few of our epoxide reactions. We have seen epoxides before in dihydroxylation, where we made the epoxide and then opened it with H3O+. So we'll represent that again and just see a couple of variations with that ring opening of the epoxide. Ethers are going to be extremely similar to alcohols. And so we're only going to see what happens with ethers in preparation and then also with reactions with acids. Okay, let's just dive into the functional group. Just a basic reminder for what a ether is. It's an oxygen sandwiched in between two carbon groups. Do not mistake it with the ester, right? This is an ether up here where the two carbon groups are going to be either alkyl, sp3, they could be aryl, they could be a benzene ring, they could be a carbon-carbon double bond, but no acyl groups, no carbonyls, right? Once we introduce the carbonyls, that becomes an ester. So to be very, very specific here, alkyls are our sp3 carbon groups, aryls are benzene, vinyl groups, you can have sp2 carbons, but they have to be carbon-carbon double bonds, not carbon-oxygen double bonds. Now, just a couple of reminders. You've seen ethers probably before throughout our studies of the SN2 reaction and the E2 reaction. THF, this molecule in the middle, was a polar aprotic solvent. Ethers are great at being polar aprotic solvents. They are fairly unreactive. They have relatively low boiling points. They participate in dipole-dipole interactions. They can be hydrogen bond acceptors. However, if we just have these as our solvents, there is no hydrogen bonding. Now, preparing an ether. We do know this reaction. It's just probably not been presented in this way before. The Williamson ether synthesis is the best approach to make ethers. What we start with is the alcohol. Now here NaH is acting as a base. That base is very reactive. Remember, we have used hydride before, and why it is a great base is because its conjugate acid is H2 gas, bubbles out of solution while Chatelier drives us forward. Now, after that acid-base step, we will be performing our old school SN2 reactions. So the first step is preparing our nucleophile, which is going to be an oxygen nucleophile. The second step is going to be trying to do an SN2 reaction. So let's just get an example up here. I'm going to hang off that hydrogen because in step number 1, Na and H, I'm going to separate them just so that we can see those two. Hydride will come in, deprotonate the alcohol, which is the most acidic proton in an alcohol. That makes an oxygen nucleophile. And then in step number 2, we should be throwing in some sort of alkyl halide. Again, when that reaction occurs, it is an SN2 reaction with a backside attack. So when we make those ethers, what's important to be able to understand is what constitutes a good base. Sodium hydride is a great base to deprotonate that alcohol. Then in step number 2, we need to make sure we understand what constitutes an SN2 reaction. If this is supposed to be an SN2 reaction, we like methyl halides or primary alkyl halides. Remember, lack of steric hindrance. We want it to be as open for that backside attack as possible. So if we're trying to think about how to create an ether, a specific ether here, MTBE here is our design, our methyl T-butyl ether. just being able to say, how do I make that ether? What we have to be able to think about is one side has to become the alkyl halide and the other side has to become our nucleophile. So looking at those two options for the alpha center here, alpha 1 or alpha 2, which one would we see in a typical SN2 reaction? Well, we would choose alpha 2 to be the actual alkyl halide. This route up on top is the best route to make the desired ether here on the right-hand side, because if we look at the other alpha, it's a tertiary, which does not work with our SN2 reactions. We would instead get an E2 reaction to occur, and that's not going to prepare our ether. So be very careful when choosing step number 2, the alkyl halide. We want it to be a methyl halide or a primary alkyl halide. We do also know that ethers can be prepared with oxymercuration, demercuration, just by using an alcohol instead of water. We were able to do that. So this is an old reaction from chapter 8. Still a good one to remember. It's just one of those in our toolbox already. Reactions of ethers. I want us to think about these as very similar to alcohols. What we just finished in chapter 12. Now, when we see these, we're only going to do acid-promoted cleavage. So that means that we're throwing in an acid, HX. We'll also see H3O plus as well as being an option. And what I want us to remind ourselves is oxygen is not the best leaving group. So we use an acid in step number 1 to do a proton transfer. We protonate that oxygen so that we can do a backside attack and have a loss of a leaving group. Now, this is going to be an SN2 reaction. We have a methyl halide or a methyl with a leaving group or a primary with a leaving group. We'll choose one at a time. Backside attack. We'll split open the ether and we make an alcohol and an alkyl halide. Now this reaction will continue to cleave both sides of the ether. It just happens one at a time. So again, we protonate. This is exactly what we just saw in chapter 12. Primaries and methyls will undergo this via an SN2 reaction after we do the proton transfer. So at the end of the day, we get 2 alkyl halides, one from each side of the ether. If you have a secondary or a tertiary, then you cleave via an SN1 mechanism. It's not very likely that we would want to do a secondary reaction here for the cleavage, simply because those are very, very slow at SN1 mechanisms. Tertiaries will undergo an SN1 mechanism rapidly because of the stability of the carbocation that forms. Now, if the R group is an aryl, benzene, or a vinyl, carbon-carbon double bond, substitution does not occur. Remember, these do not undergo our SN1 or our SN2 reactions. The SN1 and the SN2 mechanisms are only undergone if an R group is an sp3 hybridized center, not an sp2 hybridized center. Moving on to epoxides, we know how to make epoxides with the peroxy acid, MCPBA, or peroxyacetic acid were the most commonly used that we saw in chapter 8. This is a good reminder of what that epoxide functional group looks like. It's a 3-membered ring with one of those atoms being a bridged oxygen over 2 carbons. Now, epoxidation of the alkene was stereospecific, meaning that it was concerted, happened all at the same time, and when it did happen, the stereochemistry of the alkene helped us predict the stereochemistry of the product, right? So what we can see here is that if we had a cis alkene, those R groups remained cis. If we have a trans alkene, those R groups are still trans in the product. This was to understand that concerted reaction. There was no intermediate for those curved arrows that we learned. And so it's really important to remember that in those concerted reactions, that the orientation of the reactant, the alkene, will be seen in the product as well. Epoxides can also be synthesized from halohydrins. This is a new reaction that we have. By throwing in a base, we can actually get an epoxide to form. Now, when we're looking at that base, we're using hydroxide. It doesn't need to be very reactive. You can use something like NaH. That is totally fine. Stronger the better, but sodium hydroxide will do the trick. So with that first step, what we want to be able to see is that a proton transfer occurs. The base that you choose will be able to deprotonate that hydroxide, the alcohol of the halohydrin. Then the halohydrin, being in close proximity to a leaving group, will do an SN2 reaction, but it's intramolecular. Remember, intramolecular reactions are always more rapid than intermolecular reactions. So we won't see two halohydrins reacting with each other. We'll see the halohydrin reactant reacting with itself. This backside attack is seen right here in the chair structure, just so that you can visualize that yes, a backside attack could occur even in a ring formation. And then we find our final product as being the epoxide. So 2 different ways to make epoxides. MCPDA is the straightforward way, but we could also take that alkene, react it with a halohydrin reaction, Br2 in water, to make the halohydrin, and then deprotonate the alcohol of that halohydrin and do an intramolecular SN2 reaction. The outcome for either of those reactions will be the exact same. Now, last thing that we want to go over is the ring opening reactions of epoxides. Epoxides are very important in real life applications. We see epoxides be a precursor to a lot of polymerization reactions. We've talked about epoxides and how they are important for glue and that process. Because of their significant ring strain, the 3-membered ring is very, very reactive. And so it can be reactive towards weak or strong nucleophiles. We saw a weak nucleophile, H3O plus, before in chapter 8. We are going to see strong nucleophiles such as hydride reagents, alkoxide reagents, other alcohols we will also see as well as being a weak nucleophile. So strong, H-1, weak, very similar to our water. We will have an acid and an alcohol. And then alkoxides are strong nucleophiles. These are RO minuses. All right, strong nucleophiles react readily with epoxides. You do not need any sort of reactant there in the first step to be a proton transfer. You get the nucleophilic attack first. So the SN2 reaction happens first. Only time this happens is if you have a strong nucleophile. So you want to see something small and you want to see something with a negative charge. What you do also need with that is a water workup. That proton transfer needs to happen so that we take the alkoxide ion and protonate it so that we get a diol, 2 alcohols. Notice here that we are starting with a nucleophilic attack because this will always happen for strong nucleophiles. Epoxides can be opened by any of our strong nucleophiles that we saw before. O minuses, CN minus, SH minus, all of these were our nucleophiles from chapter 7. We are not going to discuss Grignard reagents, so you do not need to know about those carbon nucleophiles, and we are not going to discuss the hydride reagents. They are reactive. Carbon minus is reactive and H minus is reactive, but I'm going to stick with the nucleophiles that we had already established for ourselves in chapter 7. All of those would be regioselective, looking for the least amount of steric hindrance, just like our SN2 reaction before. Stereoselective, backside attack. So both, all of these nucleophiles would perform an SN2 reaction first, followed by that water work. Now that regioselectivity, again, let's just get a specific example here. Because we have a reactive nucleophile and we are doing an SN2 reaction, we will choose methyl groups, we will choose primaries, all over secondaries or tertiaries. So we see that nucleophile is going to attack the less substituted position and ring open. So that's where we get the nucleophile to add. Typical SN2 reaction. Now, stereoselectivity, we wanted to see that. Again, the nucleophile is reactive. We have a negative charge. That would attack the less substituted position. Happens to be a secondary here. Opens up the ring. We see backside attack must have occurred. All those lovely SN2 reaction characteristics, because that's all we're doing, an SN2 reaction. Only difference is we are attacking alpha carbon with an epoxide leaving group. All right, acidic conditions can also be used. When that is the case, when we see acidic conditions, we usually see HBr, HCl, we see water with acid, so H3O+, or an alcohol with a little bit of H2SO4. These are all weak nucleophiles, right? So when we see these guys, we want to make sure that we understand that they are undergoing an SN2 process. However, there is an influence of the SN1, and that's what we're going to see. If the epoxide is perfectly symmetrical, notice that both sides of these and these carbons are primary, then the halogen, the water, the alcohol will attack either side. Let's just walk through the reaction that we knew from before. This is a reaction from chapter 8. Proton transfer first. We are in an acid in all of these weak nucleophile cases. So this could be HX, this could be HBr, HCl, this could also be H3O+. Then water will come in and attack in an SN2 fashion, right? And ring open. And then we have that final proton transfer again to clean up our diol here and remake our catalyst. It's acid catalyzed. Now, here's the stereo and here is the regioselectivity. Under acidic conditions, the nucleophile attack still occurs at the less substituted carbon only if you are debating between a primary and a secondary carbon. Steric effects take place. So the X would appear on the less substituted, the primary over the secondary. But if we see a tertiary carbon present, that is when sterics are too high, but the carbocation influence takes over here. So even though we think that tertiaries are more sterically hindered than primaries, we will still see that halogen, that weak nucleophile, attach itself to the more substituted center due to the fact of the transition state now being influenced by a carbocation. Let's go ahead and look at that. The bond to the tertiary carbon is weaker. So if a tertiary carbon is present, the weak nucleophile will always attack at tertiary. If a tertiary carbon is not present, then steric effects are dominant. So plan of attack, tertiary is always first to be attacked for a weak nucleophile. If you do not have a tertiary, then you will attack a primary. Finally, the last carbon that you would expect to attack is the secondary. It's a little bit bonkers. However, it's determining what effect is dominant here, the electronic effect, tertiary, or the steric effect, primary. Under acidic conversion conditions, inversion of configuration is still observed, regardless of which carbon the epoxide is attacking. So there is still that SN2 reaction. Just with a tertiary, it has that electronic effect as well. So here we see a secondary versus a tertiary. We see that the alcohol attacks the tertiary, and there is an inversion of stereochemistry. The alcohol must be coming in from the backside. If we look at that leaving group on the wedge, that alcohol must have been attacking from the dash, opposites, backside attack. SN2 with SN1 influence.